In this lecture, I would like to share with you a few tutorials about the reciprocating pumps. We go for example number 1 here. For a single acting reciprocating pump, piston diameter is 150 millimeters, stroke length is 300 millimeters, rotational speed is 50 rpm, and the water is to be raised through 18 meter. Determine theoretical discharge. If the actual discharge is 4 liter per second, determine volumetric efficiency, slip, and actual power required. Take the mechanical efficiency as 80%. So in this question, we have a reciprocating pump, single acting reciprocating pumps, and then we have all the parameter here, the diameter, the stroke length, the RPM, and also the height of the pump, which is the water head, which is 18 meters. So the theoretical discharge for single acting can be calculated as using this equation. So we substitute all the value. So the A here is the cross-sectional area of the piston. So because we have a piston diameter is 150 millimeters, so we could calculate the value of A as 0.0176674 meter square. And then the Q, the flow rate, can be calculated as this one. So and then normally in pump or in common practice in flow-in pipe and so on, we will use the idea of liter per second because it is quite difficult if we say it is around 0.0044185 meter cube. So if we have it is around 4.4185 liter per second, so it is the number is quite good because we don't have we don't need to have a lot of decimal point here. So and then to calculate the volumetric efficiency, so we could calculate by using this equation. So the actual discharge divided by the theoretical discharge. From the question, we know that the actual discharge is 4 liter per second, and then the theoretical discharge is 4.4185, and then we could calculate it as 90.53%. So and then again, we could calculate the slip by using this equation, and then if we do this, we could find that the percentage of the slip is 9.47. So if we look into these numbers, we could find that why the efficiency is reduced because there are slip in the system. So these two numbers can create 100%. And then we could calculate the power required. So the equation for power is rho GQH. So and then we substitute the value of flow rate here, the Q with the actual one, 0.004. So and then we could get that the power is 706.32 watt. So and then we need to calculate what is the power required. So the word required here is actually reflect how much power that we need to supply the system to make sure that it could carry water until 18 meters. So the idea is the efficiency can be calculated as this one. We learned this in Fluid Mechanics 1 and Fluid Mechanics 2. I hope you still remember. The general equation for the efficiency is power out divided by power in. So power out means the total power that can be produced in pump system. And okay, I'm sorry. The power out is actually the power that being delivered to the water, or in actual one, we could say that the power out is actually the head of the height of water that can be delivered. So and then power in here is actually how much power that we supply to the water. So and then if the mechanical efficiency is 80%, so the equation can be written like this one. So we substitute 706 as the power out as we calculated previously, and then we could calculate the power in as 882.9 watt. So here I hope you could self-check your answer, because sometimes students are confused how to use power in and power out. So the idea of mechanical efficiency here is, you know that pump consists of shaft and so on, and then it needs to being rotated by certain mechanism. So mean pump is actually a device that supply energy. So mean pumps can run by itself. Whether you have water or not, your blade, your pump, your piston can be moved. Okay, so mean because it has its own energy. So we need to supply our pump with 882 watt, because 20% will overcome the friction. Mean mechanical efficiency 80%, we could say that 20% used to overcome friction. So because 20% of this input power need to be used to overcome the friction, means 706 watt only can be delivered as an output. So this is how we could self-check our answer in terms of efficiency. Now we will see question number 2. A single acting reciprocating pump has a plunger diameter of 125 millimeters and stroke of 300 millimeter. The length of suction pipe is 10 meter and diameter is 75 millimeters. Find acceleration head at the beginning, middle and end of suction stroke. If the suction head is 3 meter, determine the pressure head in the cylinder at the beginning of stroke when the pump runs at 30 rpm. Take atmosphere head as 10.23 meter of water. So this is reciprocating pumps, but it not use piston. So normally piston is a metal iron casting shape or iron casting parts. So it's same with the piston in engine. Okay, that's the basic idea of piston. But plunger here is something like this, and sometimes it's fabricated by plastic or a soft rubber or hard rubber, something like that. Because why we use rubber? Because we want to make sure that they are very tight at the gaps between the cylinder at the edge of the disc here. Okay, in this question, we need to calculate the acceleration head at the beginning, at the middle, and also at the end of suction. Why we need to calculate at these 3 points? Because as we know, the flow rate is not steady. So means that the velocity is not steady. That's why we could calculate the acceleration. And then the graph of the flow rate, okay, can be written like this one, a sinusoidal graph. So and then we found that sometimes it can be at this point, and at this point. So means that why we calculate as the beginning, the middle, and also at the end of suction stroke. Okay, so this is the equation. You may refer to our lecture notes today. Acceleration head on suction side can be calculated using this equation. So we have Ls as 10 meter, we have gravity, and then we have AP, cross-sectional area for piston, and we have cross-sectional area for the suction pipe. So and then the R here, R is actually the radius, but from the question it is not given. The value of R is not given, but instead of that we have the idea of stroke. So the stroke here, 300 millimeters, will reflect or will tell us the stroke length of the piston. So as I said, the stroke here is actually half of the, I'm sorry, radius is the half of the total stroke. So if we have stroke over 2 here, it will equal to the radius. So we could calculate the value of radius by using this equation. So this is the equation that we have, and then you could see that we have a cos omega t here. So and then we have a graph for cosine, okay, something like this. Okay, so this is a graph for the cosine. So means that the value is actually fluctuate from 1 at this point, and then we have a 0 here, and then we have a -1 here. So means that you need to very carefully when you calculate this one, because the value of cos omega t actually fluctuated. So and then if we substitute all the value, we will simplify this equation, means the acceleration head for suction as 4.193 cos omega t. So and then we could calculate the beginning and also the value for the middle and the end by changing the value of omega t here. So at the beginning, but you really need to understand the situation. So in this question, we asked to calculate the acceleration head for the suction part. So the suction part is start from this point. So it start from here. So the piston move to the right side. So this is the middle of the suction part. And then at this one, so this is at the end of the suction. So at here, so we found that the angle here is equal to 0. So the theta here is equal to 0. And then if we substitute the omega t or the theta here is equal to 0, so we could get the cos is equal to 1. So and then when at the middle here, so the crankshaft here is actually at the 90 degree. So the cos 90 degree will give omega t 90 degree will give us cos 0. So and then at the end means at this point, so the angle will become 180. So we have a pi here. So the cos will give us -1. So means that at the beginning, the acceleration head is positive 4.1. So this is at the middle, it's equal to 0. And at the end, it will have -4.193. So what is the meaning of this positive and negative? So you could find that at this point, suction head or the acceleration head reflect the strength of the piston to suck water inside. So at this level, so it could create a vacuum and it could suck water inside the chamber. But at this level, so at the end, so it will become negative. So means the power, the strength is actually reduced a lot. So and then we could calculate the pressure head in the cylinder. Okay, please be careful. Previously, we are calculated the acceleration head, and now we are going to calculate the pressure head in the cylinder. Okay, at the beginning here, okay, we could calculate the pressure head in the cylinder by using this equation. So we have the head of the cylinder. It is actually head of ATM, atmospheric pressure, minus the head of suction, and then we need to minus with the head of acceleration. So, and then according to the question, the head of atmospheric pressure is equal to 10.23 water. And then we minus with the head of suction. So head of suction means the height from the input water level until the center line of the piston. So this is the suction head. So and then we minus with the acceleration head. So why we need to minus all these things? So the idea is simple, because we need to create a vacuum. So vacuum means we need to create pressure which is less than the atmospheric pressure. I hope you could understand that. That is the very straightforward definition of the vacuum. So means that's why we need to minus with the suction head and also the acceleration head. If the pressure is above the atmospheric pressure, so mean the vacuum is not being created, so we will found that there are no water being sucked or being sucked in the suction pipe. So according to this calculation, so we could get it is equal to the pressure head in cylinder at the beginning is 3.037 meter absolute. Why we always use absolute here? Because to show people that we are calculating this is actually below the atmospheric pressure.